thing about bone, the reason why it's so interesting is that it's not only mechanical tissue. So it has to have certain properties that we use for building or, you know, whenever we want to build anything strong. And that's what bone is like. But it's a lot more perfect than we've ever come up with as humans. So what the techniques we use test bone and the strength of bone are actually engineering techniques or chemistry or physics. And sometimes we look at the cells. But to test materials is engineering. So the test that we're going to do is this. It's called the 3-point bending. So you have 1 point and the third point, which is there. So I need a volunteer.
Don't give it the big guy, he'll smash his way through.
I'm thinking the smallest person first. And I want you to grab this. And
like
just,
this?
Yeah, like that. Very gently, just tap it on there.
Watch Carmen's head.
Very gently, don't go too strong. Yeah, so that broke very easy, and I'll show you the difference. Yeah? That was even easier than I thought. So we put, this is a slightly different one, but after we test it, I will tell you why.
Get the big guy.
Okay? So you again, and we'll size. So just tap it. Now go stronger. Okay. Next person. Give it a go. Come on. Try to hit it right in the middle. Right there. Okay, nothing. Next person. You're going to give it a go, aren't you? Try not to break it, actually. Okay, not to break, anyway. But as you can see, it is still holding together. And the reason, because it has this in it. Now this is not all that great, is it? You can actually bend it. But when you put mineral collagen together, you get something really strong. Same basis for concrete. You put something and you hold the whole building with it. Just by putting something that is not really going to stand together alone, but the two combined together make something really, really strong. You gave it a good go at that one. I'm going to have to make another one. So, collagen and mineral work together to make a very, very strong. So this is another way to test. This is called a drop tower. And it bases by dropping a weight on a material. Yeah? So we're going to put our first material in it, which is just a piece of bone. That's just a piece of bone. Yeah? I'm going to just drop it. Both collagen and mineral together, nothing happens, and just probably dented the tin. Now, this is meant to be collagen. Every time I try, I dissolve the whole bone. So, just drop it. Look, what you see is that it absorbs the impact. Yeah. So while this one just simply this one absorbs the impact, and that's the sort of thing that you measure with this test. And now we'll put this one. This one is just mineral. If you guys go right over there so you can see it. If you blink, you'll miss it, okay? Do it again. I will see it. So if you blink, you'll miss it. Just look. Yeah. So it smashes. Oh. Could have smashed a little bit more. Yeah, so it basically turns into this. Now, the treatment of this is that we've actually gotten rid of the collagen. Yeah, and that's why it's so weak and it just breaks. It doesn't break today. Anyway, so that's a drop test, and that's how you test materials as well. It's very similar to that, but you test entirely different things. Now, if you think about it, if you were to walk around with something as heavy as this, the whole day, your bones would be, your body would be knackered, yeah? So clearly, bone is a little more intelligent than that, because if you grab a bone, it doesn't work. It's light as feather, isn't it? Yeah? Now, and the reason is for something that you have pushed into this morning. It's trabecular bone, yeah? So the bone is disposed in a way that it creates like a net. This basically distributes the weight in a very efficient manner to create something that can be light and strong at the same time. Yeah, and that's, for example, if you look at a cathedral, you see all the buttresses going about. There's many of them, and they hold the weight of the whole ceiling without actually being so big. It's the same idea for both, yeah? So, the test we're going to do now is to show how strong such a small structure can be. And we're going to do it with Maltesers. Because if you look inside a Malteser, it is exactly the same. Yeah, so it is trabecular bone inside the Malteser. Okay? So,
Malteser.
That's a Malteser, that's the chocolate. Okay. It's an electron microscope, micrograph of a Malteser. So that's the chocolate, it's kind of like the hard bit of the bone. And that's the trabecular bone, which is sort of the inside of the bone. Yeah? We'll put, I usually do this for 7-year-olds. They always ask how the Maltesers don't care about the test. So we're going to do the test, 3 Maltesers, with them in a triangle. So what we're going to do is we're going to load them, see how much weight and put on. Yeah? So if each one of you comes over and you just keep loading tins in the middle of, in between the 3. Yeah? And around it as well. So that's, yeah, still not break. Okay, that's 6 tins. This is when I start resorting to the bricks. Yeah, so we'll put that one on there. So we put a brick on. Yeah, if you let them see. Still not breaking. 3 Maltesers. I repeat. I think it probably should break now. The one at the back. So tiny Maltesers can hold the weight of tins, which is probably, I don't know how many times much more weight than they actually are. And that's how bone is so efficient. It has these 2 combined together, and not the architecture of it and how it's made that make it such a strong material, and that's why it's so perfect. And we're still trying to create for prosthesis and everything. We're still not close to coming to get something as perfect. Okay? And I think this is probably the end of the demo. Yeah? So if you have any questions, just, or you want to smash something else, you can.
Thank you.
Thank you.
Thank you.